announcement. Because the first speaker of session was missing, we are starting with slight delay, which I think is welcome for people who went to lunch anyway. I suggest now that we take our seats to begin the session. So the first speaker will be Dr. Yuriy Khalavka from this local institute and organizer. He will be speaking about tuning the quantum dots optical properties. Does it work? Okay, no, it works. This one. Okay, as a representative of host university, I really glad that you came here and that you are have considered our university as the venue for this very nice conference. As a former participant of this conference, I also think that you're doing a really great job. I mean, all the organizers who are organizing this conference, because it's really one of the biggest events I would call in Eastern Europe in terms of nanotechnology and nanochemistry. And it's my great pleasure today to tell you a few words about the things what we are working with. And we are working in our department, which is Department of Solid State Chemistry and Nanomaterials. We are working with a number of types of the material, and this is mainly because we also train students in the master degree. In former times it was nanochemistry and colloidal chemistry, but nowadays it's a chemistry with a specialization of solid state chemistry and nanochemistry. So whenever you are interested in any kind of collaboration with a student training or some extra things, that you are also welcome. But today I will talk about one type of the material, the quantum dots. And as we know that there is even an international standard organization definition for this type of material, which states actually that the quantum dots are crystalline particles that exhibit size-dependent properties due to the quantum confinement effects on the electronic states. I won't go through what quantum confinement is. So, but due to these effects, a lot of people already here know that those materials, they present specific properties that could not be just easily extrapolated from the bulk properties of any semiconductor. And if you look at the cadmium telluride, for example, which is black and which has energy gap around 1.5 electron volts in the bulk, when we make it smaller enough, up to less than 7 nanometers, let's say, we observe quantum size effects. And especially you can look at this graph where if we have 4 nanometers large particles, they will be red in color also, and they will also show the red luminescence, for example. And if you make them even 1 nanometer smaller, they turn to yellow, and even smaller particles go to blue. So basically what you can cover with those materials is kind of this part of the spectrum quite easily. But of course it would be good for many applications, and we already know that quantum dots are already used in different devices. I will show you later in which kind of devices. So it would be quite good to have a possibility to extend this range. And I would skip this because it's also known that due to the quantum size effects, nanoparticles exhibit specific absorption spectra that has certain features even at the room temperature. Like you can see here, it's a different sizes of quantum dots becoming smaller for cadmium selenide. It means also shift of the absorption maximum, which corresponds to the first and further excitonic transitions to the shorter wavelengths, basically. And Of course, you can probe those shifts with different methods. Usually, it's easiest way to do it optically, but you can also study them electrochemically due to the fact that basically the levels at which you inject electrons, they are corresponding either to LUMO, which you call it, or conduction band in this case. So as soon as the reduction of the particle starts, it should start at the potentials. It corresponds to this level, and as soon as oxidation starts, you should take away electrons from somewhere, and that's where they usually are in the semiconductor. So you observe the oxidation processes at the potentials that corresponds to the level of HOMO or at the top of the valence band. And due to this ability and the ability to show the luminescence at the room temperature, for example, they found very different applications, starting from different in vivo and in vitro bioimaging applications, and they are already sold as in principle is the marking agents for all these applications, having some advantages if you compare them to dyes. They bleach slowly, so they can be used to monitor long processes in biosystems. Some people claim that they can enhance fingerprint detections, and some forensic studies can also use them. There are a lot of attempts to create lasing from quantum dots, and it's still going on, and not all the issues are solved, but there is perspective. People use them to improve solar cell performance as luminescent light concentrators, but also there are attempts to make quantum dots solar cell by itself. And commercial thing that you can also see in Ukraine, for example, there are already at least 2 companies selling quantum dot TV sets on the market. Of course, for all of these applications, it's kind of this ability to tune the luminescence and to study it also is quite important. So I will show you a few results of our group that corresponds basically to the shift of the changes in the optical properties of this kind of materials due to the adding of some elements to the host matrix. You can call it doping. The levels we use it usually should be called maybe more properly alloying, because it's quite large concentrations. And the synthesis we use to create cadmium telluride quantum dots was developed in the mid of 90s actually. And the idea is that you use the cadmium salt in the presence of tile and the basic conditions. You create firstly you create the complex of cadmium with tiles. And then when you should inject the tellurium source, and it can vary. It can be either H2 tellurium gas purged through the solution, or it can, like here if you can see, or you can create sodium tellurides or sodium polytellurides and inject and add it. And just exchange reaction happens, and you get the core of cadmium telluride stabilized by the thiles, and because of this charge, they're quite stable, and because this bond is quite strong, basically covalent, the system itself is very stable. And afterwards you got those clusters, and to grow particles out of them, you heat it up, either for short terms, then you get pure cadmium telluride particles. If you do it longer, that partially those thiles, they start to decompose, and you can basically end up with core shell system having cadmium telluride inside and the cadmium sulfide outside. And if you want, this kind of synthesis is good because you can actually, if you want to dope your material, if you want to add some other chemicals to it, you can do it at different steps. You can either add it at the level of mixing of the components, or you can add it to clusters, or you can add it to growth, or you can actually stop the growth and add it afterwards. It depends on your desire, ideas, and so on. And here you can see the step, for example, of mercury doping, that you add the mercury ions to the clusters, and then when you start to grow, it already creates cadmium mercury telluride particles stabilized. This kind of the devices that we use, a really simple chemistry approach. So example of particular this alloying with mercury gives us opportunity to shift first the luminescence peak to the near infrared region. Like you can see here, they become broader, several peaks appear here, and if you also study it electrochemically, you can basically, with electron microscopy, you see that the size of initial particle basically do not change so much during the alloying, but only the changes of mercury content change these properties very much. And idea is here, you can see also how the live view looks like for this, but the idea is here that what is happening is, and you can see it also for cyclic voltammetry measurements, that actually you start with cadmium telluride dot and you slowly form on the surface of them, you form first the cadmium mercury telluride, and when the fusion goes into the particle, you increase the concentration, you create basically quite a complex system, which is actually could be the mercury telluride itself at the surface, one of few monolayers actually. Then in between there is something like transition, and still you have core, which is still cadmium telluride. And because particles are quite small, you can actually still see most of them in the spectra as well, and you can probe it a little bit electrochemically. And if you increase the concentration, you actually end up with something like this. So you have the mercury telluride on the top and some kind of core, which is still contains a bit of cadmium. And well, this was Mercury's story, and it gives us opportunity to shift luminescence to the infrared region. In the way to shift it to the blue region, we tried to dope cadmium telluride with manganese. Of course, there are some interesting magnetic properties expected and so on, but it's actually in water solutions. It's not a trivial task to dope cadmium telluride with manganese because of hydrolysis of manganese salts. And it's kind of quite difficult to do it, but we can somehow managed it. And what you can see here, it actually increase of the manganese in the system shifts luminescence to the blue, what you can also see from the spectra. And it's interesting because normally you expect that manganese in A2B6 semiconductors would emit from the red region that corresponds to this kind of transition. But in this case, actually, we observed an interesting point because we observed basically only excitonic luminescence. And what people say that it was shown in some cases for cadmium selenide, quantum dots doped with manganese, that actually in those systems kind of reverse energy and electron transfer occurs. So if you have quite a lot of those electrons here, they can go back, and thermally, because we are measuring at the room temperature, then it's basically go back and you observe only this kind of transition because the difference here is not very high. And so this was the way we used this doping approach to get quite remarkable luminescence in blue region. And we also studied interaction of nanoparticles of cadmium telluride with zinc ions, and with this it was kind of depending on that's why the synthesis is actually quite good, because you can actually lead the reaction or direct the reaction into different ways. And for example, if you use zinc in the form of the thiol compound, and you add it to the clusters of cadmium telluride, and you heat it up, because it takes time basically and efforts for zinc to leave this complex actually and to build to go into the particle. Basically, you end up with a core shell structure. And if you do not add any zinc, you have just growth. And if you get zinc ions not as a complex, but already after this formation of the clusters occurred, then actually it's small enough to diffuse into the particle when they grow, and you end up with basically a solid solution of zinc cadmium telluride quantum dots. And that's why actually what you observe two types of behavior for the same system. it is the same concentration of zinc. When you start with cadmium telluride itself, it's here, the black luminescence. Depending on the way you perform the reaction, your eyes can observe the blue shift here, sorry, that is corresponding to the cadmium zinc telluride due to increase of the band gap, actually. And if you do a core shell system, you kind of observe the red shift, which is due to the shell formation and the specific transitions that could occur in that case. And this would be a poster of Olena Tunkevich somewhere here around. You can talk more about this to her. And of course, being able to tune this luminescence in different directions, we tried to make some functional materials, and nowadays there is interesting approach going on because those colloidal solutions are so stable and can survive actually even very hard ionic strengths of the solution. So there is approach to create composite materials made of ionic crystal and those colloidal nanoparticles. And it works quite simple. Everybody at school, basically, you can do the same experiment when you grow crystals of rock salt or some other copper sulfate, for example, and other people, you create oversaturated solution and you let it evaporate, and it evaporates. Oversaturation leads to the growth of the crystal. You can do the same with a number of salts. Of course, they should be more or less chemically inert to the cadmium telluride, so it's usually either sodium bromide, potassium bromide, and so on. And if you leave it to evaporate, if you grow it, you can either end up, in case of sodium bromide or potassium bromide, for example, this kind of structures that are still preserving, as you see, the properties of quantum dots because they're embedded inside, and you see it like this, or you can do it with sodium, potassium dihydrogen phosphates, which is non-linear optic material, and then you come up with this kind of fancy structures due to the specific sorption of negative nanoparticles on the growing surface of potassium dihydrogen phosphate growing crystal. And actually, for both two matrices, two different behaviors occurs. In case of KDP, we observe always a blue shift, which is also size dependent. That is interesting. The smaller the particles, the larger, somehow smaller the shift here. But if you look at the sodium potassium bromide, the smaller particles, you have the larger the shift you observe, but also into the red. And this is, at least we try to explain it at the moment with help of our theory collaborators, that actually it's potassium bromide in this system because the energy gap for quantum dots are already pretty large. So this doesn't work anymore like a complete insulator, but it has kind of finite potentials. So there still could be some propagation of the electron density in the matrix, and therefore it leads to this kind of behavior. And by this I want to conclude that actually by the doping with manganese, zinc, and also mercury, we were able to extend the range of luminescences for the quantum dots of cadmium telluride quite far into the blue and quite far into the red. And if you look at this gamut figure, then actually these are colors that could be reproduced and shown and known for commercial quantum dot samples that are used in modern TV sets. And what we can achieve basically is slightly better in the green, so kind of while still more or less having the same behavior in the red, so we can even reproduce and demonstrate even more colors with our systems from the practical point of view. With this, I thank you for your attention.
Thank you very much for this very nice presentation. Now the floor is open for questions or comments.
You have shown that mercury, the second oxidation state, the oxidation state of mercury is 2. Are you sure or you have also have some in mercury 1?
Well, it's a good question. Difficult to say. I mean, I would say it's rather 2. I guess, I mean, in those conditions, the state 1 would not be really stable. But that's could be one of the ideas, actually. I need to check this in terms of electron transition that could be available in case of that. But by the other behaviors, we do not expect it. It's +1.
More questions?
So particles or animals? So particles will survive. I mean, it depends really, because I mean, it really depends. People have some studies made on them, and as far as I mean, I can be wrong in this case, but for some systems they were able to measure it for tens of minutes or maybe even hours. That I cannot be sure. We can check it with the references. And with quite high laser, for example, illumination. So this is what I can tell at the moment. We should try. We never really did any in vivo experiments at the moment with our particular particles. Therefore, we would be interested in these studies as well. But I mean, they considerably have to be more stable than dyes. But people in the dye chemistry, they're working also hard to make good dyes, better dyes, also in Ukraine. And this is kind of always discussion. And I mean, for us, it would be interesting to compare. If someone has a good in vivo system, or to do this kind of tests, you are welcome.
More questions? Actually, a very quick one. Getting back to this problem of the stability, did you compare the stability with in comparison with commercial quantum dots?
I would say no. We did some tests, but I cannot call it comparison.
So we thank our speaker again.